We started SCADA system with pressure zoning, and we have extended this SCADA system to manage our well field, as you can see in our presentation in our booth. And also we moved to handheld meter reading. We used AMR for large customers. We started using magnetic flow meters for the sources at the wells. And we did try to depart from the old way, and we thought we did everything right. But when you look at a matrix prepared by some of the people who are sitting here, this is the result. You can see that we did increase the 2.1 assessment on how we were doing and the effort we were putting in non-revenue water to 3.2, which is a good result. But we still have a lot to move on until we reach the best grade. But then we were in 2010 and before. Why would you improve any further? Everybody was telling you 20% is the best you can ever achieve. It's a good result in Jordan. It's a good result. Beyond 20%, it will become unfeasible to go down lower. But what was this based upon? What is the information that tells you that this is the reality? We still did not know many things. What is how low should we go economically and feasibly, technically? Can we go lower or not? We don't know. We don't have a water balance. How much real losses and how much apparent losses, and how much illegal use and how much metering error? We did not know. And many people do not know still today. And this is a very basic element of non-revenue water. If you don't know, you don't know how to act. And what can I do? Did I know that I can, if I want to lower this much non-revenue water, can I know that I can spend this much in this way and get this result? And back then I did not know. So we started with in different ways. One of the things we did is we approached RTI, and they had Alan Wyatt and RTI had a very useful and simple and smart model that would tell you how low can you go in non-revenue water economically by taking some measurements and some readings from the utility, plugging them in some models to simulate how leakage and how metering errors work, and you get the result that is economically measured. And we did that, and we got surprising results. We got, back then in 2011, we were 22 per, this is 2010 Aqaba City, 22.8%. The optimal was 7.5%. This is our target. But of course, when you look at it for liters per customers per day, it's a normal value. It's 100. It's an ideal value. It's not as great because we were using percentage, and when you use percentage, you don't know if you're good or bad. You don't know. You don't have a real evaluation. We also, working towards a water balance, we needed to know how the metering error, and this is some example that we started taking samples from the samples that the providers, the suppliers gave us, old meters, and testing them. And we just test meters in the field. No test bench, no consumption profile. Just go to the field and measure the errors. And we got high results. Nobody knew that you had such high percentages of errors in meters, and many people speculated that it could be the fact, but nobody can verify. So we just went and verified, and this was the result. And another good opportunity was working with the Aquanite project, which is a EU-funded project, and We had the chance to work with some experts, some of them people like Bambus and Marco Fantozzi and Stuart Hamilton, and work with other utilities in Tunisia and Egypt and Europe. So we took a pilot which is 5% of Aqaba, and we thought this will answer the questions. What is the real losses and administrative losses over there? How much money do I need to spend to get results? And the project also involved many specific tests about apparent losses, because it's a special problem that we have. And one of the things that we experienced in the project was a session where we had a support from Mr. Karalambos and Hamilton, and that support also included a visit by some suppliers of leak detection equipment. And immediately after they go home, it's made a change. People started thinking that I don't need to be unsure and speculate and wonder if this method will work and this will not. How can I do leak detection? What will work and what will not? We were certain that we had a simple way that worked in our place, and we did it, and leaks were appearing everywhere afterwards. It became very efficient. And when you do leaks, you see other problems, and you get results that save you money. So in conclusion, I think we can do well relying on whatever donor projects come on our way. We don't think about there are good practices for non-revenue water. We have to do everything. And I don't think there's a way to escape actually following and finishing and fully implementing the good practices of non-revenue water. And a way is to overcome the resistance of people to implement good practices, whether people at the high management or people or stakeholders or people inside the organization, is to actually go and make some readings. When we went and made some readings, and we got some results in cubic meter, in Jordanian dinar, this is how much we did, this is how much it cost. People started to change their minds everywhere, from inside, from outside, because they can see something that is tangible. It's not talking about the way to go and the best practices only in theory. It's something that you can do and demonstrate. And we did what works for us. We did not copy anything. And we still haven't achieved a small part of what we have yet to do to reach a good level of performance. Until we reach that 7.5 or whatever percent, that will be optimal. Thank you very much.
Thank you, Mr. Shafei. Our fourth speaker for today would be Mr. Imad Al-Dahle from Itron Metering Solutions from the United Arab Emirates. The title of the presentation would be Smart Metering Leads to Operational Efficiencies Improvements, Water Conservation and Non-Revenue Water Reduction.
presentation is smart metering leads to operational efficiencies. Improvement, water conservation reduces apparent losses in non-revenue water. This is not a sales presentation. I'm giving you facts. These are figures from Iowa. So the world demand for water by 2025 will go up 22%. 3 billion in 48 countries will face scarcity by 2025. Very serious problem. This is my favorite slide. I always use it in all my NRW presentations. So these totals are from last year. I need to update this year, hopefully, when we come out with the new ones. We've got 1.5 billion meter cube per day of production. 1.4 billion US dollars spent per day for this production. Almost 21,000 gigawatt hours per day for electricity being consumed to produce this water. 34% of it on average is lost. This is equivalent to 5.5 billion tons of CO2, which is also equivalent to 500 million cars pollution per day. That's a lot. 400 million meter cube per day is being lost. 7,000 gigawatts being lost. 4 out of 7 people are connected to water systems. So what we focus on is apparent losses. As everybody knows, non-revenue water is mainly real losses and apparent losses. So when we talk about apparent losses, we're talking about unauthorized consumption and metering inaccuracies, which is 10 to 12% of the total volume being produced as of today. Apparent losses represent 30% of overall losses. That's the estimation of what metering inaccuracies and data errors come from NRW, which is quite a big number. So how do water utilities address waste? The first one, and the most obvious one, is build more water production plants to meet the increased demand of water. Second one is to implement water loss reduction programs. The third one is to engage the end consumers in water conservation efforts. So what are the sources of apparent losses? It mainly comes from metering. So inadequate selection. It could be that the meter is oversized or undersized, and nobody really knows. It could be from aging. With aging, of course, there's loss of accuracy. And reading. You know, the meter reader, sometimes he will forget a zero or add a zero. So sometimes it's purposely misread, or there's no reading. He finds it so difficult to go and access the meter, so he won't take a reading. And this results in the wrong index of billing. Either it's underbilled or overbilled. So I don't know if anybody has heard the Internet of Things. This is a new terminology that's happening today. Cisco is doing this. First slide that all these IT companies are doing is presenting this. Basically, everything's being connected. So why not metering? The traditional meter, the dummy mechanical meter, produces only index. That's it. So now we're in a smart, everything's being smart today. Smart metering, smartphones. So we have instantaneous flow rates coming from the meter. You have, if the meter has air, you can find out there's air, there's backflow, broken pipe, and the flow distribution. Peak flows, minimum flows, leakage. So it's no longer just a dummy meter that produces just index. So why is it important? At the end of the day, you want to reduce non-revenue water, correct? You need functionalities like these. So We believe in order to do that, you need to have the full cycle from create to collect to manage to utilize and then go back again. So it's a closed cycle. Okay? Intelligence from the very beginning at every step. Data actionable starting with its creation. So from the meter down to collecting the data, make sure it's 100% reliable, 100% secure. From management of this data and coming with certain analytical tools to produce recommendations for what to do next. This is what a typical utility data workflow when it comes to metering. It should have this at least. So we're talking about data collection systems, whatever it is, if it's wireless or wired, or fixed or not fixed or mobile, it goes into the meter data collection system. Then you have on top of that umbrella is the meter data management system. And with this system, of course, you interface with different ERP solutions that are available in the utility, plus the data analytics, data export, and data access, basically. So imagine, this is a great example. If there's a utility with 100,000 customers, they are producing, if they're taking hourly data, they are producing 876 million reads per year. Where do you want to store this? How can you store this? How can you use this data? Right? So this becomes a question to be asked. So meter data collection, this is just an example of how it could be done. Okay, so it's done by using certain devices in the field where it collects it automatically every day, or it could be every hour, into certain FTP system going on with access to it, the client server architecture. So anyway, so IT is a big thing. It needs to be implemented. And it's very important for us that when you take a reading, that the time is synchronized. Otherwise, you won't be able to really take a real correct measure of the non-revenue water. It's very important. Okay. So it's just a snapshot of what the MDM system will look like. So you have meters with alarms, meters without alarms, unreachable meters, and you see the percentage, so it gives you like a full analysis of what's going on. Meters are oversized, leakage, tamper, peak flow. So, and this is just a chart of the overall. You'd see, like, for example, I think this is for a utility with an example of 1,000 customers, I think. So that's 25 million that they generated from 2013. So you can see the total water produced and built in the system and do comparisons. So what I'm doing now is giving you real examples of field examples that happened with us in the past 4 or 5 years. This is the first one, tampering and fraud example. This is coming straight from Saudi. You see here, there's positive consumption, and then all of a sudden it goes negative, and goes back again positive. And this was repeated like over 3 or 4 months. Like, okay, what's going on here? If you drill deeper, you see on the 14th, right, like, okay, so the cycle here was the 19th of July to the 19th of August. And if you see, like, the switch happened on the 15th, right? So if you drill deeper, you see on the 14th that it's still negative. And you go on the 15th, you see, oh, right, because this is hourly readings, you could see that over here in the center, somewhere at 10 or 11, is where the switch really happened. And this repeated over 3 months, and we knew that the consumer was reversing the meter. Every time the meter reader, before he comes and after he goes away, he reverses it, and he was stealing water, basically. That's illegal use of water, right? So this is just an example. If he was doing that every month, he was basically doing it for 92 meter cube. This one connection of fraud was costing the utility 1,100 meter cube per year. That's quite a lot, yeah? There's another one. These examples get better and better. All right? Leakage example 1. So you could tell if you take hourly readings, you see if you're looking at the daily the consumption pattern for day and night, you see that on every hour there's a bit of consumption. That's not possible. I mean, who's going to be, you know, using water at like 2 o'clock in the morning, or, you know, some people do, but not every hour. And this was happening already. So you knew that there was a leakage going on. It's after the meter. All right. So day 1, day 2, day 3, you could see it. And another example. This one is good. Got vacant premise. Nobody's living there. But there's half meter cube being consumed every hour. And it happened on and on and on. So this one connection costed the utility 7,000 meter cube per year. Unless if you mitigate it, of course, then it won't cost you anything. An oversizing example. I got this yesterday actually because we're working on a pilot in Oman. So I got this yesterday. I figured I'll put it in. This one is actually interesting too. So you have a connection that's, if you look at the